Okay, so this review is going to cover pretty much everything we've discussed so far this semester, and then you will have a fairly lengthy assessment over polynomials. So let's start with problem number 1. Consider the graph below and then answer the following questions. If you look at the graph, we can tell that this is definitely an odd function because if you look at the tail on the left and the tail on the right, those tails go in opposite directions. So this is definitely an odd function. And we also know that it happens to be a positive function because it is an increasing function. In other words, if you start on the left side of the graph and you work your way to the right side of the graph, notice that ultimately we increase. So this is an odd positive function. Okay. So let's get to the questions. Number 1, what is the domain and range of this function? Remember, if you can trace the graph without picking up your pencil, then the domain is all real numbers. Now, we don't have the equation here, but I do know that if I put a pencil here, I can trace this entire graph from the left side to the right side without ever having to pick up my pencil. So therefore, the domain would be all real numbers, and we could write it this way with sort of a double-sided R. That means all real numbers. Or we could use interval notation and we could say that the domain is every x value from negative infinity to positive infinity. In other words, you can pick anything you want to, and that would actually be any number, any real number, and it would actually be in the domain. Also, for this problem, the range is all real numbers because since this graph goes down forever on the left and it goes up forever on the right, and it has no gaps, every y value will eventually be covered as well. So the domain and the range for this will be all real numbers. Okay, part B wants to know about the zeros. Well, how do we find the zeros? Well, if we have the graph, all we really need to do is figure out where does the function cross the x-axis. In other words, for what values are y 0? Well, I can tell that y is 0 here, and y is 0 at the origin here, and also y is 0 on this right side. So what are the zeros? Well, those are going to be the x values for each of those 0 y values. So negative 0.816 would be a 0. Also, x is equal to 0 would be a 0. And then x is equal to 0.816 is going to be a 0. So those are the 3 zeros for this graph. Part C, describe any extrema, if any. Well, extrema occur whenever we reach a high or a low point, and we have 2 extrema. Here's one that's called a local maximum, and then here is one that is called a local minimum. They're not absolute maximums, and they're not absolute minimum values, but they are local. And to describe those, I would say, well, there is a maximum at the point negative 0.471, comma, 0.629. So I would just say that this is a max. And again, this is just a relative max. I guess I could put REL here for relative. And then, of course, here I could say I have a relative minimum at the point 0.471, comma, negative 0.629. So here would be a relative minimum. Part D, give the range of negative y values. Okay, so we have y values if we have negative y values if we are below the x-axis. And if we look at the graph, we can tell that all of these y values are going to be negative because the points are below the x-axis. Also, in this area, we have negative y values. So y values are going to occur whenever x is negative infinity all the way up to x is negative 0.816. And then we know that we have negative y values as x goes from 0 to 0.816. Okay. Again, remember the y values are negative whenever you are below the x-axis. Part E. Part E wants to know wants us to give the range of positive y values. Well, our y values are positive whenever they are above the x-axis. So it looks to me like this area here and this area here. So the y values are positive as x goes from negative 0.816 to x is 0. And then they're positive from 8.816 to infinity. So there's the range where you have positive y values. Part F, give the intervals of increase and decrease. Well, the function is increasing whenever it's climbing up, right? So we're increasing here, and we increase here. So the values of increase it's increasing on the interval where x goes from negative infinity all the way to negative 0.471. And then the graph is increasing as x goes from positive 0.471 to infinity. I still do not have my digital pen, so the handwriting still looks a little rough. Hopefully that will be straightened out after this week. But as you can see, again, it's increasing as x goes from negative infinity up to this point here. It's increasing on this interval. And then it's increasing again on this interval as x goes from 0.471 to infinity. What about decreasing? Let me change colors here. Let's look at green. We can tell that the graph is only decreasing here, right here in the middle, so to speak. So I'm going to claim that it's decreasing as x takes on the values from negative 0.471 to where x is positive 0.471. So those would be the intervals of increase and decrease. So hopefully, now that we are near the end of this unit, hopefully by now you can look at a graph and you can discuss things such as domain and range. Remember, the domain consists of the input values and the range consists of the output or the y values. Remember, the zeros are the points where y is 0, or you could say those are the points where the graph crosses the x-axis. The extreme values are any of those values on the graph where you have highs and low points. And then remember that the y values are negative if the points are below the x-axis. They're positive if they are above the x-axis. And then finally, to give the intervals of increase and decrease, just give me those x values where the graph is either climbing or going down. Those would be your intervals of increase and decrease. Let's take a look at number 2. Number 2 says to factor and then find its zeros. And we have this function here. And we know from integrated 2 that this is a quadratic. It's concave up. And luckily, the leading coefficient is 1. So that's not going to be too bad to factor. So I'm going to put my parentheses here. And remember, I can look at this sign here in front of the constant term. And since it's negative, I know that the signs are going to be different. So one is going to be positive and one is going to be negative. And I'm looking for numbers that multiply together to give me 2. Well, luckily, it has to be 2 and 1. And of course, I'm going to put an X here. And an X here. And if I FOIL this, I can see that X times X is X squared. If I do the outside and the inside, I get plus X. And then finally, positive 2 times negative 1 is negative 2. So this is factored correctly, but we also need to locate the zeros. So what am I going to do? I'm going to set this function equal to 0. And I'm going to figure out which X values would be my zeros. Well, if you multiply this number times this number and get 0, one of the numbers has to be 0. At least one of the numbers has to be 0. Well, if X plus 2 is 0, X has to be negative 2. If X minus 1 is 0, then X would have to be positive 1. In other words, the two zeros will occur at X is negative 2 and X is positive 1. Number 3 says to factor by grouping. And you should recall that when factoring by grouping, we simply group the first 2 terms together, and then we group the last 2 terms together, and then you just factor out the GCF from each group. So if we look at the first 2 terms, not only can I factor out a 3, I can also factor out an X squared. And that will leave me X plus 2. Now let's check this to make sure we did this correctly. All I'm going to do now is just distribute that 3x squared to make sure it's the same as before. Well, 3x squared times x does give me 3x cubed, and then 3x squared times positive 2 does give me positive 6x squared. So we're good there. And now if I look at these second 2 terms, I can see that 4 factors out. And that will also leave me an X plus 2. And now that we've done that, we can see that X plus 2 is a common factor in both of these terms. So I will factor out X plus 2. And once I factor that out, what we have left over is 3x squared plus 4. So we have now factored this by grouping. Now we were not asked to find the zeros, but we could. We could set this equal to 0, right? And we would get X is equal to negative 2 here. And then this one here would not be quite as easy to figure out. That would involve imaginary numbers. So we're not gonna do that part today, but I just wanted to let you know that even if you factor by grouping, you can still go further and locate zeros, which are points where the graph crosses the x-axis. Problem number 4 says to factor these special cases. And both of these are called differences of squares. We know that 6 squared is 36. So this is really the same as x squared minus 6 squared. And then this other problem is really 6x to the power of 2 minus 3 to the power of 2. So that's also a difference of squares. And the more you do these, the better you get at just noticing them by sight. I have been doing this for a long time, so obviously I have an advantage over you, but you will get plenty of practice at hopefully identifying these. And once you get used to it, they're not too bad. But since I have x squared minus 36, that will factor to be x plus 6 times x minus 6. And if I were to FOIL this, I would see that that is the same as x squared minus 36. And of course, I could set this equal to 0 and solve for the zeros, which would be negative 6 and positive 6, but that's not what we were told to do. We were just told to factor. And then if I want to factor the other side, it's going to be first base plus the second base. Multiply that times the first base minus the second base. I have made a mistake. I need to fix that. That should be a 3. And again, if I FOIL this, I will see that 6x plus 3 times 6x minus 3 is the same thing as 36x squared minus 9. But if we look ahead, we can see that we're not really done here, because I can take a 3 out of these two terms and I can take a 3 out of these two terms. And if I do that, that's going to give me 3 times 2x plus 1. That will take care of the first factor. But then I can take a 3 out of the second set. Which will leave me 3 times 2x minus 1. And then, of course, I can multiply 3 times 3. So the final answer will be 9, open parentheses, 2x plus 1, times 2x minus 1. Let me try that again. Okay. So make sure you know how to factor differences of squares. And number 5 says to simplify. This is going to cause us to have to go back and think about our properties of exponents. There's nothing we can really do with this one yet, but if you look at this one, notice that we have a square that's on the outside of parentheses, and that means that square affects everything inside. So I'm going to clear this out. I'm going to say that negative 4 squared is positive 16. And then I've got x to the power of 1 times 2. That's going to be x squared. And then I have y squared. So I have cleared out a little bit of the noise there, and then I can now multiply 3x squared y times 16x squared y squared. Well, 3 times 16 is 48. And then if I multiply x squared times x squared, that's going to cause me to add those exponents since we're multiplying, and that would give me x to the power of 4. And then I have y times y squared, and if I add those exponents, that would give me y to the power of 3. So this is the multiplied and simplified solution to number 5. So hopefully this served as a good review of most everything, if not everything we've talked about regarding polynomials. That includes doing analyses of the graphs and factoring to solve for zeros, factoring special cases, and also multiplying polynomials. One thing we did not discuss is we did not discuss polynomial division, but I'm going to make sure that we have that on our video that we see later in the block. Thank you.